Hi friends, from today onwards we are going to learn some important topics of the electrical and electronics engineering, which will be helpful for your competitive exams and to know the things about electrical and electronics engineering. So the first we can start from the transformer. As a Come to the definition of the transformer. Transformer is nothing but it is a static device which transfers electrical energy from one circuit to another circuit, and there might be a change in or without change in the voltage and without change in the frequency. So and it works on the principle of electromagnetic induction. So as I can say here, according to the definition, it is a static device and it doesn't have any movable parts. It is a static AC device which transfers electrical energy from one circuit to the another circuit without change in the voltage or with change in the voltage, and the frequency should be constant, it should not be changed, and it works on the principle of electromagnetic induction. Some important points about the transformer are, coming to the efficiency, it might be about 96 to 99% we can achieve, and it is a AC machine and it cannot operate on the DC. If you try to operate it on the DC, the number of turns, whatever the windings we can call, those windings will get burned and there is a heavy inrush of current inside the transformer, and this leads to the damage of the transformer. And just we can look at the pictorial representation of the transformer. Here we have a, square or a rectangle shaped laminated steel core. It is the theoretically we can show like this, but practically they are arranged one above the another. This is the primary side and this is the secondary side. This is primary and this is secondary. So that primary side windings, named it as a N1, those are number of turns we can say, and secondary side the load will be connected, and primary side we can connect the supply, and number of turns for the primary side are named as N1 and the secondary side we can name it as a N2. And here in the laminated steel core the flux will be created and it is moving through the secondary winding. So in the working principle of the transformer I will be explaining in detail about the working of this transformer. So let us consider ideal conditions of the transformer. What is called as ideal transformer? So here for the ideal transformer we need to neglect some of the points here. One is winding resistance, magnetic leakage and iron losses. These three are considered neglected for the ideal transformer, and for the core of the transformer, we must consider the permeability is infinite and the reluctance is zero. So these are some points to be considered for the ideal transformer. If we consider these points, then we can call it as a transformer is ideal, and we can get the efficiency around 90 to 99 to 100% of efficiency for this, because we have neglected the winding resistance, magnetic leakage, iron loss, all are neglected, so that we can achieve the 100% of efficiency without any losses. Let us consider the EMF equation. For the EMF equation, we have two EMF equations here. One is for primary side, that will be considering as a E1. So here in the picture you can look at here, whenever the supply is given to the primary side of the primary winding, the E1 is here the EMF and E2 is the EMF for the secondary side. So by theoretically if we derive the equation, we come to the conclusion that E1 is equal to 4.44 F N1 5 max in terms of volts, and here also for the E2 4.44 F N2 5 max volts. This is for ideal condition, and for the ideal condition we can consider the resistance is 0 and some points are neglected. So here the V1 voltage applied is here equal to the EMF induced, And here also V2 voltage at the secondary side is equal to EMF induced at the secondary side for the ideal condition. So that considering these two, we can write the equation as V2 divided by V1, so secondary side divided by primary side, that is equal to E2 divided by E1. So that by equations 1 and 2 we can write it as 4.44 F N2 5 max divided by 4.44 F N1 5 max. 5 max here is nothing but here flux, okay, and number of turns we can say N2 divided by N1, it is secondary side divided by primary side. And from this EMF equation we have two ratios here. One is voltage transformation ratio and current transformation ratio. Voltage transformation ratio is nothing but what? It is represented as a capital K, and it is nothing but the voltage induced in the secondary side divided by voltage induced in the primary side, that is equal to E2 divided by E1, that is equal to N2 divided by N1, number of secondary side turns divided by number of primary sides. And what about the current transformation ratio? This current transformation ratio is exactly opposite that of the voltage transformation ratio, that is 1 divided by K. So that we have here V1 V2 by V1 for the voltage transformation ratio, but here exactly it is opposite, V1 by V2, that is equal to E1 by E2 and equal to N1 by N2. But what about the current? Current is opposite to the V1 and V2, okay, so it will be equal to I2 divided by I1. Okay, from the EMF equations of primary and secondary, what are the effects of voltage and frequency? If we vary these, what is the effect on the transformer? Let us look at the equations we have taken from primary and secondary EMF equations. So let us consider here only voltage and frequency. So consider four cases I have considered here. One is voltage and frequency if you changed both in equal proportion, okay. If you changed this voltage and frequency in equal proportion, the flux density remains changed and load current are also unaffected. Flux density and load current both are unaffected here if we consider the voltage and frequency changed in equal proportion. So let us consider in the equation only voltage, let us consider E1 and E2 and F1 F frequencies keeping constant or a change. If you want to changed in a equal proportions, the flux density remains constant here or remains same. And second condition is, this is the first condition. In second condition, it is if the voltage and frequency are operated at the and considering the frequency less than the rated correspondingly reduced voltage, okay, frequency less than the rated if you considered and voltage is also reduced, not in equal proportion but some amount of proportion if you considered in the reduced manner, then iron losses will be reduced. And in the third condition we can say if it is operated at increased voltage, if we increase the voltage and frequency in the same proportion, core loss in the transformer increases to an intolerable level. So losses will be increased more if you increase voltage and frequency. Next one is if we increase the frequency with constant voltage supply. Suppose if we increase the frequency keeping voltage in constant manner, then there is a reduction in the hysteresis loss and leaving eddy current losses unaffected. Eddy current losses remains same and there is a hysteresis loss will be get reduced. So in losses section I will be explaining all these losses, that is iron loss, hysteresis loss, eddy current losses. But here four important things you need to remember is that these cases based on the voltage and frequency variations, by considering EMF equations. So first one is voltage and frequency changed in equal proportion, flux density and current are unaffected. And if frequency is considered less than the rated and voltage is also operated at the reduced manner, then iron losses will be get reduced. And in third case, if we operated the voltage at increased level and frequency also in increased level in some proportion, then losses of the core losses will be increases to intolerable level. So more core losses will be happen in this case. And suppose if we keep on increasing the frequency with maintaining the voltage constant, then there is reduction in the hysteresis losses, but eddy current losses will be as it is, those are unaffected. Thanks for watching the video, and in the next video I will be explaining the working principle of the transformer and with load and no load. Thank you.